Yeah, g'day, it's Charlie ZL2CTM. Well, I'm finally back in the shack after several weeks away on various business trips, so just getting my head back into where I got to with this this AM transmitter build. So what I thought I would do, just to sort of have a bit of a recap about where I got to and where I'm probably going to go from here. So what I'm doing at the moment, I'm just having a bit of a look at how well that modulator works, modulating a small little Class A amplifier there. So you recall coming out of the filter there from the pulse width modulator circuit over there, a varying DC. And at the moment that AM transmitter there, the input is just coming from the SIGGEN. That SIGGEN's outputting a 3.75 megahertz signal, which is where I wanted to design in the end the Class E amplifier. And then I've just got a small wire there just hanging off that 50 ohm resistor. And then that in turn has been picked up by the SDR sharp and then just being decoded up here. So if I was just to unmute that. So we are getting, or I am getting some AM modulation there. So that's good. But what I'm not particularly happy with, and why I'm probably going to go back to the drawing boards a little bit, is in regards to that varying DC. So at the moment I've got the scope there on channel A, just scoping the VCC rail for that small little Class A amplifier. So at the moment, if I was just to make sure that's on 0 and then go to DC, we can see there the DC with the amplitude modulation there, varying that DC level. And what I can see straight away, which is not right, is my understanding is to get 100% modulation, that DC level there should be varying down to 0 and up to 2 times VCC. In other words, essentially 2 divisions. And I'm definitely not getting that. So my modulation depth, even though I'm picking up quite happily on the SDR sharp and the AM receiver, I'm certainly not modulating that anywhere near where it needs to be. So that's going to force me, I think, just to go back and have a quiet think about the theory of that pulse width modulator circuit here, and what needs to change, if any, well, what needs to change to allow that output of that filter there to be, like I say, down to 0 and up to 2 times VCC. So that's all. It's all fun and games. That's how it all works. What I also did too today is just potted around and had a bit of a think about the Class E amplifier. So that Class A amplifier over there is just purely for test purposes, and eventually what's going to be here is going to be a Class E amplifier. So what I did is I took another look at, if I was just to shrink down there, that the paper that was written by Nathan Sokol at WA1HQC, and that's the same circuit I looked at a while back with the CW transmitter, this one here. So this is, I'm pretty well going to play around and have another go at that with a slightly higher power. So my thinking is this device here I'm going to use just for starters an IRF 510, potentially an IRF 540, but we'll start with a 510. Wanting to have a VCC if I can, 12 volts, just a nice simple voltage there, and then looking to have a power out of around 10 watts if that's possible. So that's the plan. So then just we sort of reviewed his various formulas there. So he goes through all the theory and then has a number of formulas here to derive what the load resistor needs to be. And I think it's just visible on the screen there, C1, C2, and then L2. So in that particular circuit there, you're required to choose a value of L1, and I'll just have a look at the what the rules of thumb need to be for that value. And like I say, you derive C1, C2 and L2 as well as R there. And R eventually will be, if for example that's around say 7 ohms, then you'll need to have a transformer there to transform that down to the common 50 ohm for the output low pass filter and the like. Anyway, so what I did is I sort of decided to do a bit of maths here, and also took advantage of some online calculators that have basically taken Nathan's formulas and turned into a nice online calculator. And one particular one is VK1SV, so I acknowledge I used his. So just sort of recapping, this is just an initial look at a classing amplifier, just sort of starting to think about what needs to be done to create that. Like I say, using those formulas you can find RL, C1, C2 and L2. I'm going to use an RF 510 just for starters to see how that goes. The full-on resistance for that particular device when it's hard on is 0.54 ohms, which we'll need. The output capacitance is going to be 81 picofarads. We need to know that because we need to take that into consideration when we look at that output capacitor C1. And its VDS maximum voltage there is 100 volts, which is also needed in looking at to make sure we don't blow it up essentially. So in terms of the online calculator, based on the formulas from Nathan, you need a Q, a value of Q, which we'll use for 5, which is a good starting value. They talk about L1, that RFC that goes up to the VCC rail, as being not so critical. What I did is I looked around in that bag of inductors I got a while back and found this one here. This one turns out to be 166 microhenries, so I'll use that for a starter, and then we'll just look at later on what its inductive reactance needs to be in regards to the load resistance. Mentioned before, use the VCC at 12 volts, looking for around 10 watts we can, frequency of 3.75 megahertz. Another value you need to throw into the calculator is the saturation voltage. So that's going to be the current flowing through the device times its on resistance, that value of 0.54 ohms there. So we can calculate the DC voltage there by dividing our power into the load by VCC. In other words, we want 10 watts. At 12 volts comes out at 0.83 amps. So 0.83 times our resistance, V equals IR, gives us a value of 0.45. So we can plug that into the calculator. Push the calculate button and we get a value of C1 of 1.296 nanofarads. Now we mentioned before the output capacitance of the RF 510 is 81 picofarads, so we have to subtract that to get our desired value of C1 of 1.215 nanofarads. That's that C1 value there. C2 comes out at 1.655 nanofarads. The value of L2 there, 1.463 microhenries. And an ultimate load across that of 6.89 ohms. Now one of the rules of thumb that I've seen a couple of times, one was a value of 30, but this one here is a value of 50. The inductive reactance of that RFC, or L1, needs to be 50 times RL. So we know that XL equals 2 pi FL, so we can work out that the inductive reactance at 3.75 megahertz for that inductor there is 3911 ohms. We said that RL was going to be 6.89, or in other words 7. 7 fives are 35, so 3500 ohms, and we've got 39 ohms, so big tick there. So I think for starters then I will use that and see how we get on. The other thing, just to double check, what I've found too from various, there's a stack of material online when it comes to the design of classy amplifiers. Another one talked about making sure that whatever device you'll use, its on time, and for the RF 510 is 8 nanofarads, that on time needs to be less than 30% of half the RF cycle. So we know that 3.75 megahertz inverse gives us a full period. Half that, so times 0.5, it's got to be less than 30, so times 0.3 comes out at 40 nanoseconds. So 8 nanoseconds there is indeed less than 30% of that. In other words, 8 is less than 40. So another big tick there. So that's as far as I've got at this stage of the game. So just, like I say, having just a bit of a think about next steps and getting my head back into where this particular project's going to go. Hopefully I'll be able to dedicate some more time over the next few weeks. So like I say, next steps are to have another look at here, find out what's going on, and see if I can actually get that output from the low pass filter to indeed be from 0 up to 2 times VCC leading into the power amplifier. And once I can get that sorted out, I'll then switch the attention back over to the Class E amplifier and see if I can't build that using an RF 510 for starters, and if that doesn't work, then potentially look at using an RF 540, which has slightly better specs in some regards. But again, the 510, in line with what I've been trying to do many times, is keep things nice and simple using readily available parts. Anyway, so there's nothing special in this particular video. It was just more just a bit of a catch-up, and just to start to think about what needs to be done next. Anyway, I'll say 73s, and we'll see you next time. Cheers all.